today's class. In this class, we will learn about work in transition, heat in transition. In other words, we can say energy in transition. In this class, we will learn about energy in transition. Okay, energy in transition. Okay, in the energy in the transition, first we will see work in a closed system or non-flow system, work in a non-flow system, right? The second one, work in a flow system, work in a flow system. Okay, next one, heat is energy in transition. Energy in transition. D. The properties of specific heat and latent heat. Latent heat. Okay, and work in flow system, also we can see free expansion process here. Okay, at this point here also we will see free expansion work, free expansion work we will see. Okay, now I will explain one by one concept. First, work in a closed system. Already we discussed in the last video reversible work. In the reversible work, what we consider? First we consider the cylinder. After that, a frictionless piston. It is considered here, and it is enclosed with air, and we consider this as a system. Okay, and a connecting rod, it is like this. Okay, if the piston and cylinder system and the boundary up to this, after adding some heat energy, the air which is present inside caused for expansion, and the expansion of gas caused for application of P pressure over the crown of the piston. After that, some displacement will exist. Okay, and integral P dV. Okay, W equal to integral P dV within the limits of V1 and V2. Okay, this will give us work done in this system. Okay, already the derivation portion is explained in the last video, right? Now, the work done is equal to integral PdV in the limits of V1 and V2. After the integration, it will give us P into V2 minus V1. Okay, V2 minus V1. Here, the work, if you consider, the work is just, it is first state to second state. Okay, that means initially this we can consider as a state 1. After the expansion of gas, the piston is moving to extreme other condition. Okay, I can say if it is top dead center, this is bottom dead center. Okay, it is horizontal, you can consider this is inside dead center, this is outside dead center. Okay, you can write inside and outside. Okay, this is inside dead center, this is outside dead center. These are the extreme conditions. Okay, initially piston at the state of inside dead center, and the air or the volume of air which is present inside having definite pressure, after receiving the heat energy, it tends to move. While it is moving only, the work is performed. Okay, once it reaches the other state, that means state 2 at ODC. Okay, there is no further work. Okay, there is no further work. Okay, that means state 1 to state 2, while the system changes its state, while the system changing its state, during that process only work is performed. Okay, suppose if you want to represent the same thing on PV diagram, this is pressure versus volume. Okay, this is state 1 and this is state 2. Okay, and the work, it may be at constant pressure, it may be at adiabatic process, it may be at polytropic process, it may be isothermal process, likewise. Okay, any type of thermodynamic process we can assume, but depending on its state and type of process, okay, type of process, the work will be done. Okay, depending on the type of process in between the first state to second state, the work will be done. Okay, therefore the work PdV this is dV, okay, within the limits of V1 and V2. We can say the area under the PV diagram that gives us work done. Okay, and it is depending on the type of process or the path in between two end points or two end states. Okay, therefore work is a path function. Okay, we need to write work is a path function. Okay, the second point you need to notate, work depends on the type of process it is followed. Okay, therefore work is an energy but it is in transition. Work is an energy but it is in transition. Therefore work is energy in transition. Work is energy in transition. Okay, next one. When it is a path function, it is not an exact differential. Okay, that means we need to show work, it is not an exact differential, therefore we need to show a cross here. It shows inexact differential. Work is inexact differential. Inexact differential. Okay, next one. One more point you need to remember. Suppose if you give the work to the system, here heat is given, okay, but work also we can impose over the system or work done by the system. These are also be there. Suppose if you consider a pump, okay, and this is a pipe, connected to this, and it is a nozzle, right? And here a piston with a rod, it is placed inside. This is the piston. Okay, and over the piston, okay, if you apply work W, okay, if you apply the work W, okay, that is work done on the system. Okay, and after that it will compress the whatever be the air present here, and that compressed air, it will come out of it. Okay, otherwise if you close it, okay, if you close this, okay, if you apply the force over the piston, it will compress the air, that is work done on the system. If you release it, then the compressed air, due to its internal energy, it will do the work on the piston and it will expand. Okay, here we need to remember the sign convention. Okay, this sign convention for throughout the subject, it is same. Okay, it will not change. Every student should remember, work done on the system is negative, work done by the system is positive. Okay, sign convention. Work done on the system, work done on the system is negative. Work done by the system, work done by the system is positive. Okay, these sign conventions also you need to remember. Okay, work in a closed system. Already we see the work in a closed system, how it is, and W equal to integral PdV. And work depends on the path in between two states, therefore work is a path function. Okay, and work is not a property. Okay, work is not a property, and the work is energy in transition. Okay, that means it is in between two states, depending on the type of process, the work that will be required or work is delivered from the system. Right? Next one, it is inexact differential. That means dW, likewise we need to show. Okay, and work done in the system, on the system is negative, work done by the system is positive. Okay, these things we need to remember. And here dW, okay, it is inexact differential. Suppose there is no meaning initial work, final work. It is not the work which is possessed at initial stage. There is no meaning at all. Okay, and work at the final point, it is no meaning at all. It is not possessed by the system, but it is in the transition. Student need to remember these points. Now we will go for the work in a flow system. This concept is over. Now we go for the work in a flow system. For that, consider a control volume. Okay, this is also a system, but when we consider flow system, then instead of system, it is appropriate, it is a control volume. Okay, this is inlet and this is outlet. Okay, and this is having L1 length, this is L1, and this is L2. This is L2. Right? And area of cross section, this one is A1, and this area of cross section, this one is A2. Okay, L1, L2, A1, A2. Okay, initially the fluid with a pressure of P1 it is entering and leaving pressure that is P2. Right, and I consider this as control volume. Right, now P1 if it is greater than P2 and due to the P1 pressure the fluid crosses the boundary, I can say this is 1 dash boundary, crosses the boundary 1 dash. After that the work the fluid is entering into the system. After that is leaving the boundary at 2 dash. Okay, that means at the boundaries it is entering, at the boundary it is leaving. Okay, therefore P1 A1 is the force and L1. Okay, this is work it is required, work it is required to enter into the system. Okay, W work is required to enter into the system. Suppose if you consider a small mass that is dm, then dm into P1 A1 L1 or dm into P1 V1. This is the work required at the inlet boundary. Work required at the inlet boundary. Right. Now, if it is leaving to leave the boundary at 2 dash, okay, that is this is 1 dash. Work required at 2 dash, okay, that is equal to P2 A2 L2. Okay, and if we consider a small mass dm, then dm into P2 A2 L2, this will give us dm into P2 V2. This is the work required at the outer boundary. Okay, here the boundary, at the boundary it is required. Therefore, work is a boundary phenomenon. Work is a boundary phenomenon. In the previous case also, by considering the boundary only we calculated the work, okay, boundary crossing, okay, therefore work is a boundary phenomena. Here, work required at the inlet boundary, work required at the outlet boundary, it is calculated. Therefore, work, total net work done, that is equal to W 2 dash minus W 1, work on 1 dash. Okay, that means work required at the outlet boundary minus work required at the inlet boundary, that is P2 V2 minus P1 V1. Okay, here at the boundaries per unit mass work required. Okay, therefore it is at the boundaries we consider. Okay, here it is a point function. It is a point function, right? But work is in transition only. Okay, work is in transition only. But here it is a point function because it is at the boundary. Okay, that there is no change of system boundaries like this. Right, okay, therefore it is the network will be given here, okay, and the flow work delivery further we will see in the first law of thermodynamics, right. This is about the flow work of a system. Now consider free expansion work. Free expansion. When we will see, say the gas is freely expanded. Now consider this is a chamber. This chamber is divided into 2 partitions and this is the partitioner. Okay, and this is having gas under pressure pressure. Okay, this is vacuum. Right. Now, if you consider this and this partition, if it is removed quickly, because suddenly the partition is removed like this, what happened? Due to the pressure difference, the gas which is present here freely expanded within the fraction of seconds. Okay? In a very small time, infinitesimal small time, the gas is freely expanded and it occupies the vacuum. What is the work done here? It is having initial stage. Okay, what is the initial stage of gas? It is there. And the final stage of gas, that is also be there. Suppose if you want to represent the same thing on the PV diagram. Okay, the initial pressure and the initial volume of the gas at stage 1. Okay, this is. Okay, after removing the partitioner, the gas suddenly expands and it occupies the vacuum within the fraction of seconds. Okay, this is the state 2. Okay, within the fraction of seconds, even though it is expanded and it occupies, it is having state 1 and state 2. The work done is 0. No work is done by that gas. Okay, work done is 0 because it is freely expanded into the other partitioner, into the vacuum. Okay, and there is no restriction for this. There is no restriction. Okay, if the restriction is there, then the work will done. Okay, it is removing, just it is expanding it there, but it will not do any work there. Suppose if there is a restriction, that restriction will push by the what it called gas. Okay, pressurized gas, and work is present there. But here, just removing, this is called as a free expansion. Expansion of gas through a large orifice or large diameter or large cross section, we can say that is a free expansion. In the case of free expansion, the work done equal to 0. Okay, in the free expansion, work done W equal to 0. Okay, and it is not a quasi-static process. Okay, 1 to 2, it is not a quasi-static process. That means it is not undergoes a series of thermodynamic equilibrium conditions. Okay, it is not passing through a series of thermodynamic equilibrium conditions. When it is undergoes a series of thermodynamic equilibrium conditions, then we can say it is a quasi-static process, but it is not a quasi-static process also. That is the reason the free expansion process always we need to show with dotted line only. Okay? Here the second point we need to note, free expansion is not a quasi-static process. Right. And another one, it need to show with dotted lines. We need to show with dotted lines. Right. Now we go for the other one. Now you may ask, sir, why we consider only one partitioner? I will provide a number of partitioners in between this pressurized chamber to vacuum, and I will remove one by one the partitioner. Yes, it is a good idea to acquire a quasi-static process at the different stages. This is the chamber, and here gas is present under pressure, right? And this is partition 1, partition 2, partition 3. Likewise, different partitions are provided. Okay, and PV diagram. This is stage 1. Okay, suppose if you remove this partition, the initial partition, I can say this is P0. Okay, if you remove the P0, then gas is expanded up to this, and it undergoes a quasi-static process and thermodynamic equilibrium uptime. Up to that we need to wait. Okay, therefore here to here. Next one. Okay, after removing P1 partitioner, the gas further expanded. Just wait a minute, it reaches a thermodynamic equilibrium condition. Then you can write that with respect to pressure and volume. Right. After the P2 partitioner, okay, again wait a minute, it will give a thermodynamic equilibrium condition. Right. Okay. After the P3 partitioner, thermodynamic equilibrium condition. Okay. Likewise, you can reach stage up to second level. Okay. After removing all the partitions. Okay. That means each and every stage we maintain a thermodynamic equilibrium condition. That means a quasi-static process we followed. Therefore, in such cases, the free expansion can represent with dot line. Okay, a continuous line. Instead of dotted lines, we can draw a continuous line in between 1 to 2 for free expansion process. Even though it is shown with what we call the continuous line, the work done equal to 0. Work done equal to 0 because there is no resistance against the expansion. Against the pressure, there is no resistance, therefore there is no work done at all. Okay, in some of the competitive tests. In a free expansion process, as represented in PV diagram as follows. What is work done? If you write that the work done equal to integral PDV, likewise if you write, it will be wrong answer. Work done equal to 0 in the free expansion process. Right. Now I go for the heat is energy in transition. Okay, I will go for the next third concept. Heat is energy in transition. Okay, heat is flow from one body to another body due to temperature difference. Okay, heat is flow from one body to another body due to temperature difference. Suppose if you consider a metallic rod, this is end A, this is end A, and this is end B. Okay, and here the temperature is 200 degree centigrade, and here the temperature is 100 degree centigrade. Okay, now the heat energy Q flow from A phase to B phase. Now heat is flow from phase A to phase B. Okay, due to temperature difference. Okay, and the temperature difference, if it is 0, then there is no flow of heat energy from A to B. Okay, we can say that is thermal equilibrium. That means due to the end conditions, due to the boundary conditions, okay, boundary at A, boundary at B are at different temperatures, that is the reason heat is flowing, right? Then this is called as a boundary phenomena, as well as the heat flow is during the temperature difference only is flow from A to B, therefore it is energy in transition. Okay, we need to note some of the points. Already I told sign convention with respect to the work. Here also we need to remember sign convention. Okay, what is sign convention? When heat is supplied to system, okay, heat is supplied to system, Okay, Q in. Okay, heat is supplied to the system, that is positive. Next, heat is rejected from the system, Q out, that is negative. Right? Okay. Now, to remember easily, actually, every student should remember when he across the thermodynamics subject. Okay. For that, for the remembering purpose only, I will give a small technique here. When heat supplied, work will be done. Okay? Heat supplied, work will be done by the system. By system. Is it not? మన heat ఇస్తేనే అక్కడ వర్క్ అనేది సిస్టమ్ చేస్తుందండి. రైట్? Both are positive. Both are positive. అంటే heat input and work done by the system is positive. Next one. Work done by work done on the system. Work done on the system. Okay. The heat will be rejected. Heat possessed by the system will reject. Okay. Both will be negative. Okay. If you remember like this, it is very easy to remember for problems purpose. Right? Okay. We saw work is energy in transition, heat is energy in transition, work and heat are the boundary phenomena. Right? Now we go for the specific heat and latent heat. Generally, students may thought that heat is energy in transition and it is not a property, it is a path function. Okay, likewise they thought, and the same thing they will implement for specific heat and latent heat also, but it is not correct. Specific heat, latent heat are point functions and those are properties of the system. Okay, specific heat and latent heat are properties of system. Okay, what is specific heat? The amount of heat energy required by unit mass to raise its temperature through 1 degree centigrade or 1 degree unit of temperature is called as specific heat. Once again I repeat this definition. The amount of heat energy required by a body to raise its temperature through 1 unit of temperature is called as a specific heat. We can write Q equal to mass into specific heat into delta T, okay, or temperature difference. Right. The specific heat C, that is equal to heat divided by mass into delta T. Okay, what is the unit for that? It is kilojoule per kg Kelvin. Okay, this is the unit for that. Okay, అంటే ఒక కేజీ మాస్ తీసుకుంటే 1 డిగ్రీ టెంపరేచర్ పెంచడానికి ఎంత హీట్ కావాలి, లేదా 1 డిగ్రీ టెంపరేచర్ తగ్గిస్తే ఎంత హీట్ రిజెక్ట్ అవుతుంది, దట్ ఈస్ నథింగ్ బట్ స్పెసిఫిక్ హీట్. ఓకేనా? నౌ సీ the specific heat is process dependent. Okay, the specific heat, if you consider solids, only one specific heat you can see. Okay, but if you go for the fluids and in the case of gases, okay, if you follow constant pressure process, different specific heat is there. We can write that as a CP, specific heat at a constant pressure process. Okay, if you go for the constant volume process, specific heat and constant volume, CV. Okay, likewise that means pressure, volume, temperature and other parameters are interdependent, and once we change one parameter, other parameters also change. Therefore, we need to keep one of the parameters or two of the parameters need to be constant and we go for the other. Okay, in such cases, in each condition, a specific heat that is given. Okay, that is the reason Cp, Cv. Likewise, it will come. Okay, that means a particular process if we follow, if we take 1 degree centigrade raise, the amount of heat required for specific mass or specific gas, it is always constant. Therefore, the specific heat is property of a system. Okay, even though it depends on a process, even though it depends on type of gas, okay, and other parameters, okay, by keeping these parameters as constant, we can say the specific heat is a property of respect to gas, right? Similarly, for latent heat, okay, what is latent heat? Latent heat of fusion, latent heat of vapor. These are there. Okay, that means while change of its state, there is no change in temperature, but still the matter will receive the heat energy. Okay, therefore latent heat, that is QL, latent heat. Okay. The total heat energy, that is equal to mass into latent heat, L. Okay, M into L. Okay, whatever be the latent heat. Latent heat per kg. Okay, the amount of heat energy required for unit mass of gas to change its state from liquid to gas or solid to liquid. Okay, that phase transformation. Okay, that is called as latent heat. That is also constant, or that is also gives a single value for a particular gas. Then it is called as a property. Okay. Similarly, heat capacity. If you take heat capacity, how we can define it is a product of mass and specific heat. That is heat capacity. Heat capacity also a property for particular gas, right? These things you need to remember. Okay, once I summarize, after that I will conclude. Now, work in a closed system, first we will see, and we conclude that work is a energy in transition and heat also energy in transition. Okay, in a closed system, integral PdV we can write. And that integral PdV, it is and that work heat, both are boundary phenomena. Okay, and there is no meaning of initial work and final work. Okay, but work is in transition, therefore integral PdV we need to write. Next one, work in the flow system at the boundaries. To cross the boundary, how much work is required? To come out of the boundary, what is the work is required? That we need to consider. P2 V2 minus P1 mu1. That is gives us work for the flow systems. Okay. Now, specific heat and latent heats are properties of the system. Right. Thank you.